Hello, I'm Simon Thompson. I work as Technical Project Director for the DAP platform at IOG, but in the past I was head of the Marlowe team, and indeed with Pablo Lamela, we invented Marlowe. Let's talk a little bit about blockchain and smart contracts in general. A blockchain is an irrefutable record of transactions involving some sort of token or cryptocurrency. The reason we can think of these things as like a currency is because we can see each transaction as recording transfer of some unit of that currency from one person to another. So it's like having a big ledger in which you write where every coin, every note has gone. Where do smart contracts come into this? Well, in the simplest case, what's happening on a blockchain is that each transaction records a single transfer of an asset. And that is done, as it were, by hand. Somebody wants to make a transfer, that transfer is then made. But you can imagine automating some of these processes by computer programs, by algorithms. And this is what a smart contract is. It's not smart. Computer programs aren't smart. They do what they're told, and only what they're told. And in a sense, they're not really contracts. They're programs that run on this blockchain. In the Cardano world, we have Plutus, which is the general purpose language for writing smart contracts. So you can write any kind of contract you like using Plutus. It will allow you to have multiple participants. It will allow you to do anything that your imagination will allow you to do. But a problem with that can be that you're not able to predict how a particular Plutus contract will behave. So because of its power, you have greater risk. And that's where Marlowe comes in. Now, one of the things that people try and do when they write smart contracts is to mimic, imitate, replace processes that go on in the real world. Now, that can be complicated because what happens in the real world is that real assets get transferred and so on. If everything is digital, then that can all be done on blockchain. And that can be done in what's called a disintermediated way on something like Cardano, where there is no trusted third party, except of course the blockchain itself, taking part in any financial transactions between a number of parties. But suppose you want to involve something from the real world. Suppose I want to sell you a dog, and somehow we want to perform that contract on blockchain. How could we do that? I could at some point give you the dog, but maybe you won't transfer the money to me, and I've lost out. Or maybe you will transfer money to me, I won't give you the dog. If we don't trust each other, we can't see how we can proceed in that situation. What we can do, however, is we may not trust each other, but we may have a trusted third party, say our friend Carol. And what we can do is perform the actions of this contract on chain. You can transfer the money to me. I can off chain give you the dog, and Carol can agree with us that what has happened, and so we can agree to, the money is put in escrow into the contract. Carol can then either give the money to you or give it back to me, depending on whether or not the dog has been transferred or not. So we're able, with some trust external to blockchain, to conduct contracts where assets in the real world are transferred. So let's just focus in a bit about what smart contracts do. As I've said, what happens, as we all know, what happens on a blockchain is that transactions are placed on that chain as a record of movement of assets. There are transactions take unspent transaction outputs and spend them, transferring their ownership potentially to other people. So this is how assets flow on the Cardano blockchain. How does a smart contract work? Well, we have to ensure that we make some stipulations about what's to happen, and that is enacted by submitting transactions to the blockchain. That's how the contract takes place. But those transactions don't come out of thin air. So on the blockchain, those transactions are submitted and checked to see that they conform to the contract, but also we have to, off the blockchain, somehow create the right transactions to be submitted and checked. So these programs, these contracts that run, have one part on-chain, one part off-chain. And as you look into the technicalities, this begins to look quite complex, quite subtle, and certainly not a space for a beginner. So how can we try and make that more accessible to someone who just wants to start and to start building some simple contracts on Cardano? The answer is, what we do is step back and say, what is it precisely we're trying to do with these smart contracts? What we said with Plutus is that we would try and build a language that would allow us to write any kind of smart contract. But perhaps we could do something different. Perhaps we could say, let's, instead of trying to solve every problem, solve problems in a particular area, a particular domain. Let's build what's called a domain-specific language. That is a language that's designed to fit with the language and the ideas and the concepts of something in the world, rather than being written in the language and concepts of the computer. We don't want to talk about variables and functions and so on. We want to talk about flows of cash. And what we decided to do with Marlowe, inspired by discussions with Charles Hoskinson, who founded IOG, is to look at designing a domain-specific language for traditional financial contracts. So RealFi, if you like. So what we want to do is look at how we can take traditional financial contracts and write them on Cardano. That means we have a much simpler language. We're not trying to solve every kind of problem, with nothing to do with NFTs, for example. But we have a language where we can express, in terms that are understandable to people who work in finance, contracts that can be run on the blockchain. And the advantage of having a more restricted language, a domain-specific language, is that we can design certain guarantees in by design. So we can make sure that the language will not allow certain kind of bad things to happen, or will make sure that certain good things always do happen. So a DSL can give us guarantees that we know whatever program you write, whatever contract you write in that language, it will have certain good properties. And in particular, what we were aiming for in designing Marlowe was to ensure that contracts would always proceed. A contract could never get stuck. You couldn't finish up with somebody being able to walk away from a contract. As you can imagine, if you and I were enacting a contract, I could make a payment into the contract, waiting for you to make a corresponding payment. You could walk away, and potentially that money of mine could sit in the contract forever. We have to design against that kind of walk-away behavior. We have to also make sure that contracts won't go on forever. We designed Marlowe so that we could be sure that contracts would only live a particular length of time, which we can read off from the contract. And we also designed it so that up front we knew who the parties to the contract were. But if you think about it, these are things that are all properties of real-world financial contracts. And what we wanted to do was mirror those properties in the language so that we were able to give those guarantees to anyone writing a program in Marlowe. So as I say, there are disadvantages, there are restrictions, but those restrictions give us advantages in that we can give you guarantees about what a Marlowe program will do. And there are also other things that we can do. Because Marlowe is limited, we're able to guarantee the properties I talked about, but we're also able to check other kinds of properties. So for example, because Marlowe contracts are essentially finite, they don't go on forever, we're able, without running a contract, to check every possible way that contract could evolve, And so we can check in advance to see that any payment the contract might want to make, anytime a contract talks about making a payment, that payment will be executed in full. No payments can fail. We can do that through what's called static analysis. There are also ways that we can use formal verification, machine-checked proof to guarantee other properties of Marlowe and how it's implemented. And those are things we're going to talk about in week 6. Okay, what is Marlowe? What can you do in Marlowe? Well, you can do a number of things. You can pay money into a contract. When I say money here, I mean a crypto asset of some sort. You can pay money out from a contract. So Marlowe can control flows of money, assets, between participants. What else does a contract do apart from have flows of assets between participants? Another crucial thing that can happen is that it can take input from the outside world, as it were. That one of the participants can be asked to make a choice about how the contract should proceed. So there is that kind of choice, and so the contract can go down different alternative paths. And that choice, while it can come from a participant, could also come from a third party. We could get information from an oracle. So, for example, we're able to take information about real-world financial exchange information, for example, and feed that into a running Marlowe contract. So Marlowe allows flows to take place, and those flows can depend on choices by participants and real-world data that comes from an oracle, an on-chain oracle. We're also, as time goes on, we're looking at transferring roles in Marlowe contracts. So when a Marlowe contract is running, just like if you're taking part in a financial instrument, in principle, you can transfer your ownership of that instrument to somebody else. We can do that by specially minted tokens in Marlowe. How do we design Marlowe in such a way that we can give the guarantees I've talked about? I've talked about ensuring that contracts don't go on forever. I've talked about how ensuring that contracts it's not possible for somebody to walk away and not interact with the contract and leave cash locked up. The answer is the contract can't reach out and take money, for example, from your wallet. The contract can't force money to be extracted, and this is a crucial point of the way that these contracts work on the UTXO model. For money to be put into a contract, you have to authorize the money coming from your wallet and going into the contract. So what happens if you don't make that authorization? Well, the answer is that the Marlowe program will have built into it a timeout. So when it asks you to authorize a transaction, it will give you a timeout. And if you don't authorize a transaction by the point of timeout, some remediating action will take place. And so therefore, at the timeout point, progress happens. The contract can't get stuck. And because of the finite nature of Marlowe, we know that there will only be however you execute the contract, there'll only be a finite number of these timeouts. And so once all those timeouts have been passed, the contract will end. And so this ensures that the contract will only go on for the period of time that we can predict. And at that point, the contracts are designed, any money that's locked in the Marlowe contract will be returned to its owners. Inside the Marlowe contract, we have local accounts, like the account model on Ethereum. But these accounts are local, they only belong inside the contract, and they are closed when the contract is terminated, and the money in each account is returned to its owner. So by design, because of timeouts, we have a finite nature of the contracts, and by design, at the end of that period, we can be sure that we will have all the money returned to the account holders as required.